So this is the panel discussion, and well, I like to think about it as a debate. In the U.S., we've gotten a lot of those in the last few weeks, and one of the things we've learned a lot about is both how high stakes it is and how big a difference it can make, how much it matters with style over substance. And having taken that lesson greatly into account, I thought about how we should organize this high-stakes debate where quantum gravity is the theme, but it's really quantum beating gravity, I think. Either unitarity wins or else equivalence principle wins. So it's a high-stakes debate. And in order for them not to do what the honorable politicians do, which is to run away from their promises, and try to twist the words of their counterparts, I asked them each to provide one slide, a one-slide policy statement. It's not the full argument, they wrote actual papers, but one slide with just brief highlights. And it has already appeared on the web. So when the slide goes away, you can still go and check and ask questions accordingly. So the way we'll do it is that they each get 5 minutes sharp, because we also want to have time for actual discussions, to present their one slide. And then after that, they can, well, throw rotten eggs at each other, and the audience can join into the fun. So, well, we started in the order that they submitted their slides, and Don was the fastest, so he gets 5 minutes.
All right, thanks. Can I have my slide?
What's the fire?
Great. All right, so thanks, Tim. So this morning, I gave our argument that if black hole evaporation is unitary, something funny has to happen near black hole horizons. And I want to remind you that the form of that argument was to consider an evaporating black hole and to consider 3 subsystems associated with it. I happen to have called them A, B, C. For purpose, in case they don't begin a discussion, they were radiation emitted early, Hawking radiation, a single outgoing mode, one outgoing mode now, and the Hawking partner mode. Okay. I then went through really just some algebra, so the following inequality is true in any quantum mechanical theory. The inequality is that if when combining systems A and B, the total von Neumann entropy is equal to or less than the von Neumann entropy of A, it must be true that the von Neumann entropy of the combined system B with C is bigger than or equal to a half the von Neumann entropy of B. Okay. I claim that that result implies that, well, if the evaporation is unitary, there will be a time when combining B with A causes the entropy to decrease, so this is satisfied. So the output is this, but an infalling observer, if they are to see the usual vacuum state as they cross the horizon, should see a pure state, one in which SBC is 0. On the other hand, if quantum field theory in the usual sense holds near the horizon, this mode certainly carries out some non-trivial information or has non-zero entropy, so this inequality is violated. That was my argument. Okay? So I want to mention 2 things about this. One is I feel compelled to comment very briefly on Juan's talk, because I think he claimed in his talk that he presented a model that violated this result, that satisfied this, but which was consistent with both. Well, okay, so our conclusion is that if the theory is unitary, something has to break down at the horizon. In fact, the usual semi-classical approximation has to break down either at macroscopic distances outside the black hole. I used quantum field theory outside the black hole to evolve this mode B, or for infalling observers crossing the horizon. I think Juan claimed in his talk that his model satisfied this and also satisfied both 1 and 2, But I think in later discussions, Juan and I have agreed that the model does not obviously satisfy at least one of those two postulates stated up there. So it's not a counter, is that fair? Yeah, okay. I just felt I should inform the audience of at least some progress in our discussion. So the main point I wanted to make, though, is that when I presented the argument earlier today, I talked about one mode, and as a result, this violation of, for example, usual quantum field theory seen by infalling observers might be thought of as a small effect. You might think it was just the presence of maybe one extra particle in this mode over the entire black hole. I wanted to emphasize that a given infalling observer is exposed to a large number of modes coming out of the black hole. I talked about a mode that has a certain shape, say this yellow region. It corresponds to a Hawking particle that will actually be emitted at a certain time. But of course, there are all the Hawking particles, there are the modes corresponding to all Hawking particles that will be emitted for quite a long time in the future. Those modes are still present in blue shifted form near the horizon, and my infalling observer intercepts them. Okay? And if you count up how many modes there are, say just that are S waves around the black hole, ranging from that Hawking mode that is becoming a real particle now at a distance r from the black hole, down to some Planck scale cutoff, the number of such modes is r log r, or r log r over L Planck. So it becomes parametrically large as L Planck goes to 0.
That will be 5 minutes.
That's 5 minutes already? Okay, so, oops. In fact, since there are a lot more than S waves coming out of the black hole, or modes that could be there near the horizon, there are a lot of particles that bounce around near the horizon trapped by the angular momentum barrier, the actual number of modes that an observer can sample is this times r squared, which is a very large number. And as a result, I and my collaborators feel that all the effects of this kind must be large. That's really what I'm going to say. That's not a theorem, that's an opinion, but one I would be very happy to make.
Theory, not fact. Just like evolution, right? Oh, what is it? So, well, Steve has 5 minutes.
So I think Don and I agree on points 1 and 2, so those are not unique to the firewall scenario. And it's been explained in a very mathematical way, but there's a very simple intuition that if you have a semi-classical black hole geometry, basically you've got to get the information out from behind the horizon somehow into the outgoing stuff. And that is non-local with respect to the semi-classical geometry. Though geometry may not be the fundamentally correct way of thinking about things. Okay, so that's I'll take that as a starting point, that to have unitary evolution, you need something like that, and the question is characterizing it. And it seems to me that there are logically distinct scenarios. I'm going to divide the scenarios in a coarse way into 2 logically distinct sort of scenarios. The first, I'm picturing these in the Eddington-Finkelstein type picture. The first is the massive remnant, or fuzzball, or firewall picture. And they all are quite similar in the following way. So you imagine that you start out with an initial black hole, which has some regularized version of the singularity in the horizon. And then at some point, the surface of your object, massive remnant, fuzzball, or firewall, has to emerge from the black hole horizon. And then you have something that isn't a black hole anymore. It has some kind of surface. And so that's a common picture, I think, to all 3 scenarios. And one of the consequences of that is after that transition has occurred, then if somebody falls in, they will experience pain when they hit that surface. It is not an innocuous thing. And so that's one way of characterizing this scenario. I think in contrast to another possible scenario, and I should emphasize this scenario as well as the other scenario involve non-locality in the sense that information is being relayed outside the light cone. Here, this surface as it's emerging, the surface of the object is traveling in a space-like fashion. So another alternative I think we should consider and try to understand, if it is possible, I've proposed models for how it could be possible. It's a form of nonviolent non-locality, where say you have some information that goes into your black hole or your black hole forms, and it's, of course, in the full quantum theory of gravity, regular inside. Somehow the information has to get out, and the idea is that it should be transmitted in a more innocuous fashion into modes near the horizon, but not ultra blue shifted. And one can at least parameterize scenarios where that happens, parameterize models where that happens, where this is innocuous to the infalling observer. The kind of thing you need is of order 1 photon emitted, or 1 graviton, per light crossing time. And each of those gravitons can have an energy, or sorry, a wavelength of order of the radius of the black hole. And that's a very innocuous thing if you're able to get the information out in those modes. And so that's the proposal that we think about, this sort of non-violent non-locality. That's a less radical picture in my mind, unless it's shown to be inconsistent. And so we should be trying to understand what consistent physics might describe this latter picture, which is closer to true black hole behavior. It's closer to the picture where the thing at the center of the galaxy is a black hole, not a firewall. In fact, in my mind, trying to describe the physics, which may not be founded on space-time, but perhaps on a more general picture of Hilbert space networks, trying to understand how such physics could work would be a guide to the underlying laws of quantum gravity. And that's the essence of my statement. I imagine it's close to this.
Great, and we will take questions. We will take questions. Find the website so you can see arguments. And then it's Lárus coming up with 5 minutes.
Okay. Yeah, so let me perhaps, two things that I want to state here. But one is that when we have, in the original formulation of black hole complementarity, we did have 3 postulates for black hole evolution. And it was clearly stated in the paper that these referred to observations made by outside observers. It did not refer to, we were not trying to come up with a unitary phenomenological, a phenomenological description of an underlying unitary evolution that was describing the experiences of an infalling observer. They were actually very much focused on the outside. We introduced this stretched horizon. So up there I have a picture of this. The green thing is the stretched horizon, which the microscopic stretched horizon we said would be 1 unit away. And then we said outside this you will have a semi-classical description. That semi-classical description is going to involve some, in terms of the usual type of effective field theory, you would think. Now if you have an effective field theory that includes a Lagrangian, which we don't really know there, but for this, and then a cutoff. And so if we're working with a cutoff that's lower than the Planck scale, then of course this stretched horizon has to be placed accordingly further out. And this effective field theory, it describes, it uses local equations outside this stretched horizon, and then there is some complicated unspecified dynamics that's going on in the stretched horizon that does the trick for us of actually bringing out. Those actually is supposed to implement this non-violent non-locality that Steve was referring to. Okay. Now, in this effective theory, this surface is expected to be quite hot. In fact, it's going to be at a Planck temperature. So it is certainly a firewall. All infalling observers will be absorbed by this stretched horizon. They'll be thermalized and they'll be subsequently be emitted. And then if we want to talk about the system that, for example, Hawking modes, those Hawking modes are actually, from this point of view, they are simply emitted from this hot surface, or alternatively, you can imagine some pair creation outside it, but then the ingoing partner of the pair will be absorbed by the stretched horizon, and it will have the same end result, that you have an outgoing state of the black hole. And then what happens after that actually will depend on the dynamics of the black hole, of the stretched horizon. If it is such that this, the information about this mode that was going in is pretty much immediately emitted, so that it doesn't actually get to entangle with the rest of it. So basically, it'll be absorbed into some local area of the stretched horizon to begin with, one imagines. And if it doesn't manage to thermalize with the rest of the system before it is emitted, then it will not get entangled with the rest of the black hole state, and then you will presumably have a firewall. If, on the other hand, it takes time before the information comes back out, or the entanglement with the outgoing mode, then you may avoid that. If, on the other hand, you want to actually insist on talking about experiences of informing observer, this is not a good language for that. Because as soon as they hit the stretched horizon and before they hit the global horizon, or even enter the black hole, they are in fact absorbed into the stretched horizon. They become a rather non-local and difficult description. And so you would have to formulate another effective theory, if you wish. That's indicated there. There's one of these nice slices that we talked about. They are nice in the sense that they avoid strong curvature regions, at least as long as the black hole is large. They are nowhere are they is the extrinsic curvature large. But these things can be constructed in a straightforward way. But their global properties are not so nice. And as was argued by Steve and Matt Lippert, and also by David Lowe and myself, once you take into account the large boost that occurs between the region where the infloating observer is passing through the horizon and where our friend Bob is sitting and doing their measurements, and then they're not so nice. You will actually get gravitational back reaction that undermines the validity of the local filter, and then you can take the story from there.
Thank you. So I think it would be great to have the three panelists sitting up here, all of them with faces in this direction, so that both of you can see their grimaces when the other people say things that don't make any sense. And
tomatoes may be properly
So, questions? I can flip the slides, but you can also check them if you're preparing questions online. Right? They should be up there.
questions from them.
You can ask questions to each other too, you know. But,
Well, I'll start if no one else is ready. So, Lárus, I'm just trying to digest your slide here. And does your last point mean that you are happy with the conclusion that the infalling observer does not experience what we think of as normal low energy effective field theory? Do you think you've given an excuse why that doesn't happen?
No, they will. No, that's actually not what we concluded. But what we concluded is that if you apply local effective field theory on these slices, in fact, we analyzed a version of the this Alice Bob Charlie Gedanken experiment, which led us to the conclusion that if you were going to use local effective field theory on these nice slices, they would actually be extremely uncomfortable. They would, in fact, be projected into a unique state, which is, I think, what you call a firewall. On the other hand, we then, once we had reached that conclusion, we started looking about for reasons why we should not believe that conclusion. And that we found because, in addition to the usual criteria that you apply to decide whether you're going to believe in effective field theory, that is, whether you have strong curvature effects or whether you have strongly tensor surfaces, we claim there's an additional criterion which is non-local in nature, which comes from these back reaction effects. If that is not satisfied, I'm simply not worried that I concluded that I've got into. And then we actually further considered the system, and we asked the question, what happens now if we never allow our slices to bend more than so that these global effects don't come into play, then you find that by the time that you can do, by the time that you can do, that you can read anything out of the Hawking radiation, and I will give you, I'll grant you, you could be working with an old black hole so that it's really only the scrambling time. At that point, we would conclude on such slices that the infalling observer would indeed be in the process of being wiped. But this turns out to be also when that slice is unavoidably bumping up against the singularity inside the black hole, where you're not surprised that they get uncomfortable.
So I still don't know whether you're agreeing with what I said or disagreeing with what I said.
I am agreeing with you that something very dramatic will happen to an infalling observer.
Okay.
In the context of the effective field theory that we proposed originally, that is the effective field theory of the outside observers. That is where the stretched horizon is this Planck temperature membrane.
Yes.
And it is certainly very dramatic
Yes.
from the point of view of the infalling observer never makes it past it. It in fact gets thermalized, it gets then re-emitted in Hawking radiation. I am also claiming that if you then try to analyze the system on an infall where you adapted your effective field theory to be appropriate to describe the infalling observer using local observables rather than these very strange horizon observables, then that observer it actually will not require, it will require precisely the sort of non-violent, non-local effects to avoid the conclusion, yes, that we have.
I see. So you agree with both Steve and I.
No, I don't agree with you that you would, an infalling observer, if I were to have the misfortune to fall into the black hole at the center of the galaxy, I believe I could have a few days or weeks to worry about my fate.
During which time you would experience physics indistinguishable from that approximately flat space, or you could measure these non-local effects?
Early on, I would have a very hard time measuring them because according to our estimates, where we tried to use ADS-CFT, they were exponentially suppressed in the entropy into the minus S effects. And so it's hard to do, of course, quantitative estimates when you don't know the theory that you're working with.
It is indeed.
And but this was as first we could do. It seemed to us that early on in this evolution, you would not run into. Basically, we could put it this way. What I would claim is that if you're calculating, for example, 2-point functions or 3-point functions,
Yes.
you should not see going through the horizon. You should only detect that when you're doing some very special some high-end point function.
I wanted to drive at this from a different angle. There's something about complementarity that has troubled me over time, and I've tried to spell that out in various places. So it's the following. So complementarity is a pretty big departure from the usual Hawking story or the refinement of it that is the nice slice description, the semi-classical description. It's a really big departure from it. It's a form of non-locality. It's a very non-local breakdown of the quantum field theory, and seems quite radical. And I think one question is whether consistency requires complementarity. And again, I mean something like Bohr complementarity, where you have different descriptions, and I think that was present in your original paper, different descriptions for outside observers and inside observers. So is that truly required for a consistent picture, or is it possible that there are consistent pictures, perhaps gauges, where you can talk about both inside observables and outside observables, but where you do have some perhaps relatively mild non-local effects that in the end account for the information transfer out of the black hole. So I've tried to pin down various complementarians on this question. Is complementarity logically necessary? And I'd be interested to hear an answer from you, Lars, or anyone else who thinks they have it.
Well, I think it would be presumptuous of anyone to think that they covered all possible logical eventualities. I think it was proposed as a way to, first of all, these postulates that we talked about and this description in terms of a stretched horizon was intended as an argument that you did not have to give up unitarity in this story. And that, of course, left us with the obvious issue of the infolding observer. And complementarity, as stated, was that I believe is simply saying that there is not a contradiction in saying that you can pass unharmed through the horizon and yet have all the information come out in the Hawking radiation. It was deliberately or necessarily extremely vague about how this was going to go on, since we did not have, and we still do not have, models. So I think if you come up with a model that does what you say, I don't think we would have any problem.
I might add that if you believe in firewalls, I think that there's no Xeroxing paradox to start with. I think it's impossible to draw a Cauchy surface that intercepts both copies of the data, which is weakly.
But it's the firewall.
Well, the firewall is used someplace where the curvature of space line is large, and everything's sort of specified with a sort of curvature. So you know it's firewall.
As I understand it, you really would like to have both the horizon and smooth surface. I mean, I think this is you need the horizon as a smooth surface to have you have to have the temperature, to have the entropy, to have most of the properties we know of black holes. Once you don't have to give up of the horizon as a smooth surface, then all bets are off. It maybe behave thermally, maybe it doesn't, maybe it explodes, maybe, I don't know, maybe that's a prediction that black holes after R times log RS explode. So that's consistent with the firewall proposal. And yeah, so that's I think
Well, it's not really
point.
consistent if you believe at least that the black hole, that the entry of black holes is given by the Bekenstein-Hawking.
Yeah, that's not valid anymore once you have a firewall, because the Hawking-Bekenstein formula depends on that surface.
Well, some other explanation in defense of something like a firewall picture, although I clearly would like to attack it. But in defense of that, if you have some microstates with the right entropy, with the right density of states, the right entropy counting, however you get it, then you'll and have the right kind of mixing and so on, and you'll have something very close to thermodynamics.
Let me also
The
remind you that
logic that leads to Bekenstein requires the horizon being smooth. I mean, for example, the Euclidean continuation.
Yes. Yeah, you need another way to compute S Bekenstein something.
Yeah, well, it may not be the case. Maybe that's the prediction. The prediction might be that after this time, it's not the Bekenstein-Hawking entropy. There's no reason why we should think it is once there is a singularity in the horizon.
Maybe it stops radiating, it's a remnant. It's right there. After. Laura?
So I've asked you this, but I also want to ask other people. In black hole complementarity, if you have this picture that a typical quanta is coming up, and you put a mirror and reflect it back, do you really expect this to have a universal infall in the sense of not seeing anything? So it was carrying out information. You put a mirror and it has free infall. A typical quanta. That's the picture of black hole complementarity.
So this was a question to Lárus.
Well, anybody. Like,
But it's within the context of complementarity.
yes, yes. So, I mean, what was the idea in black hole complementarity? That information is being carried out by, and what's understood now, information is being carried out by typical quanta of Hawking wavelength, and you put a mirror, it reflected back, and it has free infall. I mean, while coming out, it knows about the structure of the state, it knows something, and while going back, it has a universe. I mean, I just find it a bit, I would have thought there's some scale difference, that if you have energy much greater than the typical quanta, it may have a universal behavior, but if you take the typical ones, it cannot see the black hole. It will see the structure.
Well, I mean, if you try to reflect on it, you say, well, we have a hard time getting back in.
If you, sorry,
Simply have a hard time getting, it has a wavelength that's comparable to the size of the black hole.
so it doesn't even come out from inside you. I mean, if it is hard time doing
Well,
that.
some do. There's a tail, right? It's exponentially small in the. I would have thought that complementarians would answer that from the point of view of an outside description, at least well, to quote Lenny, or hopefully not to misquote him anyway. The picture is that you have something very much like a hot membrane in the outside complementary picture, and things burn up there, so I don't see why it would be different or something that is reflected back.
Simply be absorbed by the stretched horizon
Yeah.
and re-emitted.
Sure. If I make an observer from those nodes, what would be their experience while following? That's what I want to ask. In their own frame, the typical quantized frame.
I think complementarity suggests by the word wants to have both things. Wants to have the unitary description. I mean, this idea of having something at the surface of the horizon works nicely in classical physics, and people have discussed it in that context. And this is a version where it would work also in a full quantum description.
So you're agreeing with the idea that it will have a universal infall in its own frame.
Well, and then just the word complementary means that there is the other description where it would fall in. So yeah, it would fall in.
Well, it's the ultimate free lunch. I mean, you eat your cake, lose weight,
Yeah,
that sort of
that's
thing.
what
Actually, I'm not
You know,
sure if I-
lower taxes, increase expenses, it just,
I'm not sure if I understand the origin of the question, because you're talking about something that comes out and is reflected back. Is there some reason that that would be different from something that you just threw in?
No, I just meant that if you told me that there's typical quanta at some scale, and I throw something much higher energy, and it will have a universal behavior, I can buy that. But something which is coming out and carrying information, and I throw in something of the same scale in, and it has a universal behavior, I just don't find it. I think that's where fuzzballs differ. That they say that these guys have time experience, the typical ones, and the high energy ones have a universal experience. But there's a scale difference in it. I mean, I just wanted to know what your opinion is.
maybe I could turn that question a little bit. Oh, sorry, for you. Okay. No, there.
Well, that's the right question. Well, I'm just trying to imagine how we could do some calculations to actually test some of these proposals. I mean, so, in ADS-CFT with black holes, most of the calculations we actually do involve internal black holes, or Euclidean. So, well, I mean, Don, for example, do you claim that are these effects absent for internal black holes?
I think
or-
they're absent for eternal black holes.
So I mean, there's not necessarily any contradiction with any calculation that's been done in
That's right.
ADS-CFT.
That's right.
But if you think in ADS-CFT you could form some black hole from collapse, and if these effects potentially extend outside the horizon, like you think about gravitational waves and so on, and then I can actually imagine doing some, even like 2-point function calculation and
Yes.
seeing some deviations in the
Yes,
geometry.
I mean, it's important to say that in our story, there are two possibilities. Either there's deviations from usual low-energy vector field theory outside the horizon, or something funny happens for an infalling observer. In that second option, there may be an effect that's only visible exactly the moment when they cross the horizon. And it could be, it's consistent with our analysis, that nothing funny happens outside the horizon at all. In that case, it's going to be awfully hard to see it in a standard, straightforward ADS-CFT calculation. But yes, the other alternative, that something funny happens near the black hole, is
I mean, it's a bit hard to, the CFT is just thermalization that's occurring, so
That's right.
it almost seems to predict that something unexpected has to happen during thermalization or something. I mean,
great, you agree with us, wonderful.
yeah, I mean, that,
Is that what are you saying something strange would happen during thermalization?
I did question, what do you mean by strange? I thought that was terribly second.
Okay.
it seems like a prediction that if you were to believe that the effects extend outside the horizon, not just right at the horizon, then that must translate into some statement about thermalization.
Yes, it would.
Yeah, but that would be an issue of the dictionary. But from the field theory point of view, they should not. Yeah, even if this firewall effect exists, from the field theory point of view, it does not necessarily implies anything non-trivial with thermalization. It may just means that there's a subtlety when we translate the dictionary, and just how you translate the states.
Well, you
From
would
the
think that
geometric
things like
language.
the 2-point function is parasite.
I thought, I'm surprised. I thought that you were going to say that you see the same as we ordinarily see outside, but that we wouldn't be able to reconstruct the inside.
Yeah, right.
Well,
So
this,
that's
this
what
is
you
my
were
preferred
going to say.
conclusion, is that there are two possibilities logically. One is that something happens outside, and the other is that nothing happens except when you cross the horizon. My personal preferred conclusion is that nothing happens until you look inside, so it's reconstructing the inside, which is difficult. But the other possibility is a logical option. And if I understand correctly, some people in the audience, like Lárus from the fuzzball community, would advocate that it's the something happens outside option that's realized. So at least that version of the fuzzball conjecture may be testable in ADS-CFT.
There's a warm-up problem to all of this, which we've struggled with over the years, which is finding good observables to sort of reconstruct the local bulk, right? And it seems to me you really have to go after those, do the warm-up problem before you can attack the question of what kinds of observables are sensitive to what happens as you locally fall across the horizon. Otherwise, one is just looking at something roughly analogous to the S matrix, right, where you have stuff coming in, stuff coming out. And,
I mean, you do things like look at very high mass operators in geodesics and things like that, where it's really
yeah, there have been lots of attempts in various directions to reconstruct bulk physics in a careful way. That's one.
And those geodesic approximations have known concerns if you're looking at them in a time-dependent backward as opposed to the eternal black hole. It's harder to use those as reference physics. Speaking of which, since you asked about eternal black holes, I did want to say that the reason I think there's no firewall for an eternal black hole is two things. One is that it's a very special state, which is an exact time translation symmetry, so it's not subject to aging in the normal sense. The other is that we usually describe it in ADS-CFT as a very particular kind of entangled state. And as far as I can tell, the full set of states of that type is some small fraction of the space of all possible black hole microstates, so it doesn't have to have the same behavior as a typical state.
So you might throw matter into the eternal black hole and chirp it away from time cancellation and still.
Depends how much matter you throw in. So the eternal black hole that we're thinking of has a kind of wormhole inside it. And the neck of the wormhole in the default case is the same size as the black hole horizon. The more matter you throw in, the bigger the horizon gets relative to the wormhole. Okay. I haven't actually calculated where I think the threshold is, but if you make the horizon size much bigger than the maximum neck of the wormhole, then I think it does age and will develop effectively a firewall. Okay, but that's the parameter that controls the issue. So there's a context where the Euclidean calculations probably do make sense, and at least we firewall promoters would still agree there's a smooth horizon and the calculation can be done for the magnitude quantum metric.
So I wanted to bring up the subject that people really don't seem to like, which is fuzzballs. There's universal agreement that that's a terrible idea. And, at least among the panels. But I think that's a little bit harsh in that if you interpret that in the weaker sense, namely that it's not semi-classical geometries necessarily, but it's simply an estimate of how large a typical quantum wave function is among those that contribute to the black hole, and saying that those are not actually very small near the singularity, they're around the size of the black hole, it would seem like a more conservative thing. So my question is to Steve, actually. You were saying that you preferred, as the most conservative, something non-violent, non-locality. Is that, are you sure that's not it? That fuzzballs can't be a realization of such conservative, non-violent, non-locality?
Well, fuzzballs have been, at least those, well, the picture of fuzzballs describing Schwarzschild-like black holes has been kind of a moving target. We don't have a precise description.
Well, it's not like the other things are that precise.
Okay, well, let's talk about what has been said. And so a typical picture is that you have states of string theory or geometry that have a lot of structure just outside the horizon. So you don't have a horizon anymore. And you've got, say, superposition of a lot of these states and so on that gives you your fuzzball. And so there's a large microscopic variation between all these different states. It is a microstructure. To me, it seems that it's something that's a little bit like other familiar objects that we see, where you have a superposition of a lot of states outside of us, like stars or neutron stars and so on. And when you have something like that, where you have a complicated, say, superposition of states with a lot of microstructure outside the horizon, it seems to me that it's very, very difficult to encounter that, say, in free fall, without having a painful experience. Now, the fuzzball community, and Samir in particular, have argued, well, maybe there is some magic that occurs there. So I can sail through the surface of a fuzzball, and I've transitioned from an outside state into a fuzzball state, but I don't know it. I'm still,
Fair enough, but it's
diving into a pool of water from 100 meters, but I just keep going
It's
through
a
it.
concrete context in which one can investigate perhaps whether complementarity is in fact realized because there is no concrete realization, or is a firewall actually realized
Well,
because
is
there
it a
is no
concrete context?
realization.
Because we don't have a description
No,
yet.
I think if you think that the firewall, the fastball is that is some microscopic description, such that when you fall in, you feel nothing. That's like ADS-CFT. I mean, it's like any microscopic description. There is some description somewhere, right?
Well, it's
We don't say
inspired
what it
clearly
is.
by
What?
ADS. It's something that's inspired by ADS-CFT.
Right, but these are microscopic things which is not geometry. I mean, or if it is geometry, it's not felt like geometry for normal people. So let's call it not geometry because, right? I mean,
I would say it's not.
it's not felt by normal people. I mean, we are normal people. We could fall into a black hole and we would feel this geometry. So we would try to measure it. We wouldn't be able to measure this microscopic geometry. So we would measure the Schwarzschild geometry.
Okay, yeah, you're saying the superposition of,
Yeah,
will
well,
look
it's
like-
some microstate, so,
Yeah.
so
Yeah.
then, I
that's
think
the
this
hope.
is more or less the standard, well, I think, well, in some sense it's the, I mean, I think that's, one thing ADS-CFT tells us is that there are some microstates that describe the black hole, and somehow, the observer that falls in feels the Schwarzschild geometry. Or matrix theory, or whatever, whatever might.
Well, good question, because we don't know how to describe what the observer's falling is.
Yeah, so we're assuming, we're making this assumption that we think that what we calculate using the standard geometry is what the observer falls in will see. Now, if we just are going to say what is geometry, but it doesn't behave like geometry, well, it's just something.
Something non-trivial has to happen. Maybe it does happen, but something very, very non-trivial, I think, has to happen in order for an infalling observer, say, our size, encountering a solar-sized black hole, to fall through that without being disrupted. Something special has to happen. Maybe it does, and maybe it is an alpha state in the CFT, but it seems to me that that's a rather strong assumption that needs to be.
No, I'm not saying I'm saying if you have a black hole in ADS, right, if we believe in ADS-CFT, we have a microscopic description. Right? It's gluons on the boundary, so that's the microscopic description. Okay. Now, we can call this microscopic description fastball. We can call it whatever. It's not geometric. There is no geometry. Okay. And then in addition, there is something which is a geometry, which is the Schwarzschild geometry in the interior. That's the only geometry that, well, we think it's relevant for an observer who falls in. So I think we need to go from this microscopic description to this geometry, or some other microscopic description and the geometry. Right? That's.
Yeah, I think the fuzzball plane is more falsifiable than that. It's saying that for very high energy observer, I'm saying there's a scale, there's a temperature scale. So for energies much higher than that, such a quantum falling in, such a Unruh-David detector falling in will not click. But on the other hand, I'm also saying that for very low energy, like of the typical quanta, it doesn't see any geometry. So for intermediate scales, you would say that there's more and more of emergent space. So it's not like there's one geometry. That's only for very high energy observers. So it's probe dependent, I think. So it's a bit more falsifiable.
Well, let's consider a lower energy quantum, right? The quantum of order the temperature.
Mm-hmm.
So So we could imagine a situation where we do a calculation, let's say, area. For example, the calculations that Son et al. Did for calculating the viscosity. Those involve quanta which are the order of temperature, or even local wavelength. And they give results which are agree with both the field theory and with the Schwarzschild geometry.
Yeah.
So I take that as evidence, as saying that the Schwarzschild geometry is relevant for this low energy quanta also. That in order to really calculate what's going on, you need to solve the wave equation of those low energy quanta in the Schwarzschild geometry, not in some other microstate geometry.
But that gives you a thermal description. But to get a statistical description, I think this decoupling limit that has to be taken for the D1, for the ADS-CFT may hold a key, but I don't know. Okay, I think it's a little more falsifiable. That's all I was saying. That it's not. It may be wrong, but I think it's a bit more falsifiable.
I think one saying it's been falsified.
The statement you made is falsified, I think. The statement you made is falsified. Maybe there is a similar statement that might not be. Right? I mean, you made the statement that low energy quantum will not fill the Schwarzschild geometry. But it is crucial for the low energy quanta to fill that geometry to derive hydrodynamics, to derive all the things we could derive.
I think there's some subtlety in the decoupling limit, but I don't want to. I mean, say that. I mean, okay. For now, I'll take what you say.
I think, by the way, one of the challenges, again, and this is repeating the point that I made in response to Per's question, one of the challenges is we don't yet understand, in another way of saying it, how to decode the hologram, right? And describe local bulk physics in terms of boundary physics and understand how that works at a very detailed level. Something we've struggled with in all these years since you introduced your wonderful
That's one thing I was trying to do this morning, how it could work. So
That's right.
So how the interior modes could be consistent, how you could get them. So
Yeah, I
interior which fundamentally doesn't happen.
I want to emphasize this kind of toy model building is very important. I mean, there's been a lot of discussion about fuzzballs, and maybe there's a soft landing for high energy observers thinking fuzzball. Steve likes to talk about, what's your phrase?
non-violent,
Non-violent, non-locality. But as far as I can tell, there are no complete models of either of these. In the following sense, right? In the firewall context, the thing that makes it a strong firewall is the fact that you've got a lot of modes interacting. As I said, it's not just the S-wave modes that Steve talked about as carrying out the information. There's this huge set of higher partial waves, which also can potentially carry information out of the black hole. And as far as I know, there is no model of either fuzzballs or non-violent, non-locality.
or firewalls. Right?
Or
We're
firewalls.
applying a double standard.
Wait, let me finish my statement. There's no model of that, there's no toy model of that, which takes into account all these modes and shows that you can have a non-violent effect.
There's also, well, okay, so in defense of that viewpoint,
Yes. So you're saying your point about firewall models, it's trivial. There's just no insight into the black hole, and there's nothing to model, and the observer burns up.
So
Well,
some
come on,
of
you
the
don't have a-
firewalls
okay,
have
wait,
become
wait.
the default. I mean,
What's that?
The war is the default.
There's
We
a
know
double,
that.
there's a double
The
standard
question
here.
is, we all agree there has to be an effect. My issue is, can it actually be non-violent?
Okay, so one of the things, I'll talk about it more in my talk, is try to parameterize the physics in a description where you have interacting quantum subsystems with a larger system, subsystem corresponding to the black hole, a subsystem corresponding to the outside. We have models for these quantum subsystems, say just from the local quantum field theory description, that we know have to be modified because Hawking's description is wrong. And so you can try to parameterize departures from Hawking's description. That's one of the things I've tried to do. Now, yes, there is not a complete dynamical description, but there are toy models parameterizing the kind of information transfer that you need. They're not complete, but on the other hand, we're taking small steps to try to find a way to a consistent resolution.
So I'm not asking
Let me just finish.
Okay.
And I would say, to object that they aren't complete, to me doesn't doesn't make sense when you're advocating a picture that also is not complete. In order to form a firewall, you need some kind of pretty radical non-locality. What's the deeper dynamics behind that? I don't know. Okay, so
My
that's,
objection is not
we're just
the
trying to
model is-
parameterize different.
My objection is not that the model is not complete. My objection is that it appears that an important piece of physics for determining the strength or the violence of the effect may be the inclusion of all the higher partial waves. And that's a particular ingredient which has not been included in the model so far. So I don't trust the conclusion that the effect can be non-violent until I see that effect incorporated.
But one could just as well flip the argument in the direction of saying you can't necessarily conclude that a firewall is the only consistent solution.
As I have agreed.
Okay. So these are things we need to explore. And I think, one of my goals has been trying to understand whether we can give a consistent description of something that is non-violent. And there's some initial proposals in that direction, which admittedly are not a complete.
So this is my challenge, the next small step, is include the higher partial waves and let's see what happens.
Lars?
Can I maybe just make a point that's quite different, but I think many of us are quite convinced that the black hole evolution is unitary because we can embed the problem into an ADS-CFT context. We can, for example, consider the formation and evaporation of what you call a small black hole in ADS-CFT. And then at the same time, in ADS-CFT, we do have a real, it is, as has been mentioned, a real challenge to formulate a local description of space-time physics. And in fact, from talks we've had earlier in this program, the best people expect to see is to perhaps get such a local description in the strict n goes to infinity limit. And then as soon as you are talking about a finite n, but large, you expect there to be non-localities, and there will be, for example, if they are non-perturbative in the 1 over n expansion, I believe you will find that they will go like e to the minus the entropy of the black hole, and those are precisely the magnitude of non-local effects. I think we believe we need to get the information out of the interior of the black hole in a non-violent fashion. And it will, of course, be, from the point of view of, this will not be something that you would see in a strictly local effective fusion that is described in the following observers. But I don't see that we have to, that we should even be insisting on that, since we're basing our faith in unitarity here on a formulation which is in terms of non-geometric reasonableness, as Juan said, the glue on something.
The way the non-locality enters, though, well, it's experiment dependent. Let's think about a finite g squared n situation. So let's take g squared n to be such that the radius of ADS is 10 to the 10 light years. Okay. Then, I think if the conjecture, the ADS-CFT proposal is true to in the strongest form, you can recover all of the local bulk physics down to, say, sub inverse TeV scale, whatever we can throw. Then you have pretty small departures from locality for describing the physics, certainly to that scale and so on. But on the other hand, if you form a large enough black hole, then you expect significant departures from locality over that black hole, over the radius scale of that black hole. So where it enters depends on, for example, whether you're scattering at high energy, etc. Again, if ADS-CFT is true, if there's a holographic description of our world, curvature scales are really big, and we have correspondingly very small effects when we're describing, say, LHC physics.
More questions?
question from a distant observer. I want to know, like, there's the four postulates, and then there comes a derivation, and then there's a contradiction formulated. Like, are there any additional assumptions on the way in the derivations that people might or might not agree upon? So on top of these four postulates, and after the discussion this morning, I got the feeling that there's additional assumptions that maybe were taken for granted, which are not the case, or
I think it's just unitary. You can also drop that. You can decide that Blackwell Ranch is not unitary.
so you say I assume nothing on top of these four postulates.
Except for, well, unitary is one of the postulates.
That's what's possible.
That's right.
Well, some of us would say.
Oh, sorry.
Three postulates.
Right.
There was one additional assumption, which I stressed in my talk, but I will remind you. I made the assumption that the dynamics of the stretched horizon is causal. The other alternative is that you have some observer who sits outside. The stretched horizon knows before the observer makes his decision whether he's going to fall in or not. And then that unleashes another can of worms in the physics.
This is not an entirely innocuous thing, because if you look at the classical stretched horizon, it is actually acausal, in the sense that it is actually, we refer to it as teleological. You sort of have to know the whole history of the black hole to actually know where it is. And
That's because the event horizon is defined by a future boundary. Right. It's a mathematical construction, and yet you can still solve for any of the physics locally causal, which you have to solve for these equations.
By the way, this nonviolent non-locality, or whatever people like to call it, is actually departing at the level of assumptions. Namely, one of the assumptions is it's all local quantum field theory outside the Schwarzschild radius. And I think that's one of the assumptions we might question, certainly once we know that we're apparently in a place where we need to deal with some non-local physics, like we would extend outside the horizon as well.
So more questions, or we originally planned to, I think, 75-minute debate, but maybe we can, we can cut it off, if there were questions have been settled.
But I have a post question, or maybe more clarification. Like, so what are you each saying about what happens to the black hole after the peak time? That's when the firewalls you set in, right?
Or earlier.
So, are you saying that you can describe the black hole using semi-classical physics after the peak time? Each of you?
I'm certainly not saying that if you're talking about the experiments of infalling observer.
Yeah.
Something, as I say, is going to go wrong with semi-classical physics, at least after the page time, whether it happens outside the black hole or as applied to the infalling observer crossing the horizon. I can't tell you for sure which one, but something's going to go wrong.
I'm suggesting that certainly something happens by the page time, because you need to start relaying the information out. The proposal is that is not necessarily violent to an infalling observer.
Yeah.
It could be measurable with extremely careful measurements by an infalling observer. Say, again, think of an infalling observer falling in, and you've got to alter order 1 outgoing graviton per light crossing time, and the typical wavelength of the graviton modes that need to be altered are under the size of the black hole. So that's, you've got a few extra quanta of that kind coming out, but how many gravitons have we been able to see as the human race? So it's these can be very innocuous, I think.
So you're really saying
Even if
that
they're protons.
the whole calculation of forking already breaks down around the page time?
I think that's necessary, actually, because if you look at what, that goes back, in fact, to Page's arguments. If the entropy is going to drop back down to zero so that in the end you have unitary evolution, by the time you reach the Page time, you have to start having an order 1 effect.
But that order
The
1
right
effect
point.
involves knowing all the particles, right? Involves tracking calculation over a long time.
Well, there's an order 1 effect for each light crossing time after the Page time. You need 1 bit of quantum information to come out. So in that sense, it's something, it's something. It's 1 bit per almost per Hawking quantum.
It's 1 bit that has to come out, but it has to come out once you know that it could be entangled in a complicated way with the rest. So when you do Hawking's calculation, if you think of that as a calculation you do over a short time.
Well, if you view it in the frame of the infalling observer, then there has to be an order 1 discrepancy from the natural vacuum state.
It's like flipping 1 bit for each Hawking quantum that comes out, roughly after
The thing is that the infalling observer, so that's the infalling observer comes in and measures a bunch of things that are so can make a bunch of measurements which involve only a subset of the Hilbert space, because an infalling observer cannot make measurements on S things. You can only make measurements on less than S things.
That's right.
So if I take an analogous system, like gas in a room, and I make measurements only in some little corner, and the gas is in a perfectly pure state, whatever, I'm not going to see something that differs from the thermal state. I only make measurements on the
the analog of the Page time is making measurements on more than half of the room.
Well, that's the point. But the observer who falls in makes measurements only on a little corner of the room. In order to make the measurements on the whole room, you have to compare. You need to have done Hawking's calculation over all this very long time, get track, and so on. Right? And it's not clear that quantum field theory allows you to do that, because the effective coupling of quantum field theory is L Planck squared divided by R Schwarzschild squared, right? 1 over S. So that's the effective coupling of the field theory. And normally when we do calculations in quantum field theory that involve more than 1 over G squared quanta, we are in trouble. I mean, the people who do calculations for the LHC and they have n gluons, they start getting in trouble because they don't know, for example, things like their normalization bond, or they see already ambiguities when they involve large numbers of quanta.
But we don't have to involve large numbers of quanta. You have this guy who falls in. All he has to do is sample the outgoing Hawking mode and the ingoing Hawking mode and see whether or not they're perfectly correlated.
Right. So that involves a small number of quanta.
That's correct.
And if I base my intuition on ordinary systems, where even if it's a big enough system, when I measure only a small number of quanta, it could be perfectly thermal, despite the whole system being pure. When I make small numbers.
So the point is that, okay, either the infalling observer finds a result which looks pure, or he finds something which is not the local vacuum state and has significant deviations from semi-classical physics.
Yeah, so I would say finding the vacuum state is what, first of all, is what reproduces the usual thermodynamics.
Yeah.
Therefore, I would equate that. So I would equate seeing the usual vacuum state to seeing the typical thing, right?
Right, except that it has a very different property than your example of the gas molecules, because you said in gas molecules, you take 2 degrees of freedom, any 2 degrees of freedom, and you study them as a joint system, they are not in a pure state, whereas the local vacuum state, the infaller, is in a pure state. This is a good summary of the problem.
Well, those small number of degrees of freedom are in approximately pure state.
I think if you try to parameterize, and again, that's something I've done, try to parameterize the information transfer that's needed, say in these bit models, you sort of see what's going on. You see that, well, unless there's some other way of getting the correct information flow rate, but it looks like basically you do have to alter the state of one Hawking quantum per light crossing time in a significant way. I think that's important. save you that there are a lot of people.
You might only need to have put in the right face. I mean, that might be all.
Yes, we're trying to study these parameterizations. Because I
Well,
think
there's one
they
very
can
concrete thing. Well, maybe I should repeat this. But this calculating the 2-point function at long times, right? This is a concrete thing where you calculate one very concrete observable. It involves a small number of quanta, but you can really see the difference between unitary and non-unitary.
Yeah, there it's small, though.
Yeah, there it is small.
A better thing to do is, okay, you take the black hole that's evaporating, or maybe it's not better, but it's one thing. You take the black hole that's evaporating and actually measure the first, whatever, S over 2 quanta, the first half of the quanta. And, you can effectively project into a definite state for those quanta if you perform enough experiments. You can choose the one where they come out in a definite state. Quantum tomography. And then ask what happens to the subsequent, what the subsequent quanta coming out look like. And so there you perform this, it's very much unlike a 2-point function. It's more like your many-point function. But just go into that state where you have definite projection for the first half, and then the remaining ones coming out have to be lined
Yeah,
up.
that could be that could produce weird answers in the remaining part, because I mean,
But we can do it.
but if you project, well, if it is a typical state, I wouldn't expect anything strange. But if it's atypical states, you could produce funny features in the future. Like,
Well, let's say it's a typical state that you do project on a definite state. Definite state. I think.
yeah, so, yeah, I would imagine if it's a typical state, I would get continue to have a black hole, yeah. But well, this is an assumption, in this case it's wrong.
Several panelists are nodding at the same time.
It would be great.
That was 20 years.
Maybe we're nodding. We're jet lagged, we're nodding off.
More questions? I could see Roberto looking suspicious, but no.
Well, just one final question, sort of a follow-up to my question before, like, I mean, so is it then, I mean, are you saying that basically you don't know any of the black hole properties of the black hole after the next time, and we have to figure that out by maybe studying a DCFT, I mean, you have some guesses or proposals for what would happen, but basically we don't know, and if we study a DCFT perhaps carefully enough, we can find out, or what do you say?
Well, I'm proposing to parameterize our ignorance, constrain it by things that we know or believe, and unfortunately I don't see how to get the answer out of ADS-CFT.
But in principle,
In ADS-CFT, we'll see. So, that's been a big challenge.
My sense on the vigor of the debate that it's time to call it a day. Thank the panelists. We're voting. We don't. Oh.
You vote by writing papers.
This is true. I mean, they have all put up a clear platform, so maybe one should have a poll.
So it's complementarity.
Not secret. Take pictures.
You're actually talking
Yeah, I should use galactic.
Yes.
You forgot Postulates.
I forgot. I did not forget. There are no panelists who have defended that position.
But you attempted.
But also, it's not so, the more options there are, the best here it is that they're all distinct.
That's true.
Right? Complementarity, we could put at the bottom and say all of the above.
What if we erase firewalls and write none of the above?
None of the above. Very
More
good.
obviously orthogonal.
All right. So we'll start from the top. And hey, don't be wimps, right? Everybody votes, and it's a democracy. You vote once.
We're writing down names.
So, firewalls. Thank you, David. You gave a lovely persuasive talk. You got a voter. Okay. Non-violent, non-locality. 2, 4, 6, 8, 9. Complementarity. 2, 3, 5. Oh my God. None of the above will win big. So, none of the above.
What
Well,
about the ourselves? Are you voting?
Well, yeah, I voted for complementarity. 6, 8,
David, you voted twice.
12.
The first was a mercy vote.
Are you going to an actual fraud for that? It's still a 28. It's a, well, that's a very close approximation. I think we're 30. Okay, well, there you go. None of the above. Huh? There's still a long way to go. Next time you need a panelist that's. Okay. So now I guess we can go home, go for dinner, right?